we're going to be doing problem 17-100. The basic premise of the problem is a man rotating inside a culvert, and since the man is moving inside the culvert, the center of gravity is not at the center of the culvert. So to account for that, we're going to just draw some free body diagrams and kinetic diagrams to start. Okay, so for the free body diagram, we have the center of gravity here at point G, and then we also have a normal force and a frictional force, and we'll call this point A. And then for the kinetic diagram, we're going to have at G an MAX and MAY, and then we also have the rotation of the culvert because the man is moving, so we'll call it IG, and then we also have up here omega, the angular velocity of the rotation of the culvert.
Okay, so now we're going to take a look at the components of acceleration, both translational and rotational, of point G. And we're going to do this with respect to point O. Point G is the center of gravity, and point O is the center of the culvert. So we're going to start in the x direction, and we're going to have acceleration of G, x direction, is equal to acceleration of point O minus radius, which we're going to denote this as R1. R1 is the distance from O to G, which is 0.5. And we're going to have that times omega squared. This is a relative acceleration equation, and we're going to plug in for omega and R1, which both actually happen to be 0.5. And so this gives us AG in the x direction being equal to AO minus 0.125. Okay, so now we're going to turn our focus to the y direction. So we're going to have acceleration of point G in the y direction, and that's going to be equal to AO plus 0.5 alpha. And we left alpha in terms of itself rather than converting it to the radius and angular velocity. So looking at this term right here in the y direction, A0 doesn't translate in the y direction, so we can have that term go to 0. So AG y is going to be just equal to 0.5 alpha. And alpha is what we're looking for. So looking at this, we're going to need to find a way to eliminate one of these variables. The reason being is when we go to put it into our equation of motion for rigid bodies, we don't want to have two variables. We only want to have one so we can solve. So what we're going to do is we're going to look at the acceleration of point O with respect to point Z, and then hopefully we can relate the acceleration of O in terms of angular acceleration. So we're going to write acceleration of Z is equal to acceleration of O minus R alpha. Okay, so because AZ doesn't slip, we can eliminate the acceleration term for Z. So that's just going to be 0. And so we're going to have A0 ending up being equal to 4 alpha. And the radius in this case is the radius of the whole culvert. which is just equal to 4. And so, which is also the distance between O and Z. Okay, so we've skipped a few steps. But basically what I did during the break is I wrote acceleration of point G in the x direction in terms of alpha and what we had before. So that's now equal to 4 alpha minus 0.125. And I've gone ahead and written out our equation of motion. And so we have all these terms now, except for IG, and that's pretty simple to get. All that's equal to is the mass, which is, because we're in English units, we need to divide 500 pounds, which is the total weight, times 32.2. We're going to multiply that by the radius of gyration squared. And when we punch that out, we get IG being equal to 190.2. And that's going to be slug feet squared. Okay, so now all that really is left is to plug in or into our equation of motion. So what we have now, and I'm going to go ahead and write this in blue. We're going to have 500, which is our weight right here, and that's going to be multiplied by R1, which is the distance of point G to point Z down here. And so we're going to have that times 0.5, and then that's going to be equal to our mass moment, which we just found, multiplied by the angular acceleration, which is what we're solving for. And then our next term is going to be this term right here, and that's going to be the mass, which is 500 over 32.2. And then now, because we want to be able to solve, we're going to put our acceleration term in the terms that we solved for before. So for this, which we're doing in the x direction, we're going to have 4 alpha minus 0.125. Okay, and we also need the distance r, which is going to be the distance from G to Z in the vertical direction, because we're taking the moment. So that's going to be 4. Okay, and then we're going to do our term y, which is going to be that's going to be pretty similar. It's going to be 500 divided by 32.2, which is the mass. And then we're going to write our acceleration how we did before, which is right here. So we're going to have 0.5 alpha. And then we're looking for R1, which is the distance, the horizontal distance here of G to Z. And that turns out to be 0.5. Okay, so now it's just an easy case of solving for alpha. I'm not going to go into explicit detail, but when you punch it all out and you get alpha, you get 0.5